Hello everyone, and thank you for attending today's webinar. Static versus Dynamic Chemisorption, Insights from 2 Case Studies of Platinum-Alumina Catalysts. My name is Jeff Kenvin and I'm the Vice President of Science at Micromeritics and the moderator for this webinar. Before we begin, we wanted to cover a few housekeeping items. At the bottom of your screen are multiple engagement tools you can use. You may expand your slide area or maximize it to full screen by clicking on the arrows in the top right corner. If you have any questions during the webcast, you can submit them through the Q&A. We'll try to answer these during the webcast, but if we run out of time, it will be answered later via email. Additional materials are available in the resource list. We encourage you to download any resources or links that you may find useful. Some networks cause slides to advance more slowly than others, so logging off your VPN is recommended. If your slides are behind, pushing F5 on your keyboard will refresh the page. If you experience any problems during the session, you can find answers to some common technical issues located in the Help Engagement tool at the bottom of your screen. An on-demand version of the webcast will be available after today's webcast and will be emailed to you once the session has concluded. I'm pleased to introduce today's speaker, Phong Vuong. Phong attended Kennesaw State University for his undergraduate degree and Georgia State University for a master's degree, both in chemistry. Phong joined Micromeritics in 2023 as an analyst in the PTA lab and was promoted to the position of Applications Scientist in 2024. His expertise includes techniques for particle size and chemisorption. Phong, it is an honor for me today to introduce you. We're so glad you could be here to share your insights on static versus dynamic chemisorption. Insights from 2 case studies of platinum-alumina catalysts.
Hello everyone, and welcome to today's webinar on static versus dynamic chemisorption. My name is Phong Vuong. The goal of today's section is to give you a simple and clear way to visualize how different conditions can influence your experimental results. Today's agenda will cover the basic concepts needed to differentiate between Physisorption and Chemisorption. We will also take a closer look at how metal dispersion is measured and explore the differences between static and dynamic chemisorption techniques. Additionally, we will present 3 case studies. The first case study focuses on the reusability of our platinum-alumina support. The second examines how oxygen affects metal dispersion measurements, and the third looks at the impact of reduction temperature on metal dispersion. Physisorption is a phenomenon in which adsorbate gases are attracted to the surface of a material by van der Waals forces, such as dipole-dipole interactions. As a result, no chemical bond formation occurs. Due to the physical nature of the interaction between the adsorbate and the solid surface, the process does not require activation energy. The figure below illustrates the Physisorption process. At a relatively low pressure, around 10 to the negative 3, adsorption begins. As pressure increases, a monolayer forms on the solid surface. With further pressure increase, multiple layers conform. Physisorption is considered a random process. meaning there are no specific active sites that the adsorbate preferentially attached to. It is important to note that temperature, pressure, and surface structure can all influence gas adsorption. From this brief introduction to Physisorption, the key points to remember are: it involves weak interactions, requires no energy barrier, occurs through random motion, conform multiple layers, and is non-specific. That was Physisorption. Now let's discuss Chemisorption. Chemisorption typically refers to a process involving chemical reactions where bond formation occurs due to the rearrangement of electrons. In chemisorption, the adsorbate gas interacts with specific binding sites on the surface of a solid, facilitating chemical reactions. Unlike Physisorption, where adsorbate can form multiple layers, chemisorption is an irreversible process, requires activation energy, and occurs in a single layer on the solid surface. Here are the key points to remember about chemisorption. Reactions occur at specific active sites. Only a monolayer is formed, and activation energy is required. Before diving into how carbon monoxide gas bind to platinum metal, let's first review how chemical bonds are formed. Consider a single atom, in this case carbon. Carbon has discrete energy levels where its electrons may be located, which are referred to as atomic orbitals. An atom can combine its atomic orbitals through hybridization to form molecular orbitals. In the case of carbon monoxide, when carbon and oxygen atoms combine, they split into two types of energy states: bonding and anti-bonding orbitals. Only the overlap of the lower energy bonding orbitals leads to the formation of molecule. The carbon donates its lone pair from 2p sigma orbital to generate a sigma bond, and then the 2p pi star orbital from carbon accepts back donation electrons from one of the d orbitals in the middle. Two things happen. The carbon-oxygen bond is weakened, and the metal-carbon bond is strengthened. Hence, when this type of back bonding is present, the ligand is bound tightly to the metal. Here's an example. Platinum has a half-filled electron configuration of 6s1 5d9. From the molecular orbital diagram, carbon donates 2 electrons from its 2p sigma orbital to the half-filled d orbital of platinum, resulting in metal-carbon molecular orbital overlap. Additionally, the 2p pi star orbital carbon accepts electrons from back donation by one of the d orbitals, leading to further orbital overlap. Supported metal catalysts are widely used in various industrial processes, and their catalytic activity is directly related to the active surface area per unit volume. Controlling the dispersion of metal particles on the support is crucial because it determines the amount of metal available on the surface that can actively participate in the reaction. Consequently, metal dispersion is a fundamental characteristic of metal catalysts. When discussing metal dispersion, we refer to the ratio of the number of exposed surface atoms to the total number of atoms present in the metal. For example, if the metal dispersion is 1, this indicates that 100% of the deposit metal atoms are available to participate in the chemical reaction. But what happens if the dispersion is less than 1? Consider platinum, which is often deposited as a cluster on a support material. On the left figure, the yellow circles represent platinum atoms dispersed on an alumina support. However, the right figure depicts a more realistic scenario. Only the platinum particles on the surface, shown as green circles, are actively involved in the chemical reaction. Any platinum particles buried inside the clusters which are not exposed to the surface do not contribute to reaction. Therefore, only a fraction of the total deposit metal is involved in the reaction with adsorptive molecules. Today's webinar will focus on two of the most commonly used methods for determining the metal dispersion of catalysts, static and dynamic chemisorption. The probe gases typically used are carbon monoxide or hydrogen. Let's begin with static or volumetric chemisorption, a method you may be familiar with. In a static chemisorption experiment, it is crucial to ensure that the sample has a clean surface before performing any analysis. For this webinar, we will use our standard reference material, the Platinum-Alumina catalyst, and carbon monoxide as a probe gas. The first step usually involves evacuating the sample while heating it. The sample is then activated at 400 Celsius with hydrogen gas for about 30 minutes, followed by an evacuation step. Afterward, the sample is cooled to the analysis temperature of 35 Celsius, at which point we can begin collecting the first CO isotherm. The first isotherm contains both strongly bound CO chemisorption and weakly bound CO physisorption. Once the first isotherm is collected, a vacuum is applied to remove any weakly bound CO physisorption. The process is then repeated to obtain the second isotherm, since CO chemisorption is more difficult to remove. The second isotherm will primarily reflect the CO physisorption. By subtracting the second isotherm from the first at each pressure point, we can isolate the volume of CO chemisorption. The dynamic chemisorption process is relatively straightforward. Similar to static chemisorption, the first step involves cleaning the surface of the platinum-alumina catalyst, followed by a reduction reaction at 400 Celsius. Once the catalyst has been reduced to its reduced state, a purging step is employed to remove any remaining hydrogen gas. The sample is then cooled to the analysis temperature of 35 Celsius. The analysis begins by posing a known amount of probe gas into the system until the reaction reaches the saturation state. The following animation illustrates what happens inside the test tube. The green dots represent the probe gas molecules. The red dots represent the exposed platinum crystallines, and the blue dots represent the probe gas bound to the surface of the platinum. On stage 1, most gas is absorbed and a very small amount of gas passed through the detector. As you can see, a very small peak appears. In stage 2, sample is partially saturated with probe gas. Less gas is absorbed and more passes through the detector. Hence, you will be able to see a larger peak appear on the graph. Stage 3, sample is fully saturated. All of the incoming gas will pass through the detector, hence you see a sharper peak on the graph. So let's look at the first pose. When hydrogen gas is injected into the system, it is completely consumed by the platinum catalyst. This suggests that all available surface sites on the catalyst are actively engaging with the hydrogen and absorbing it. On the graph, there is no peak after the injection, indicating that no unreacted or residual hydrogen is eluted from the system, meaning it is fully absorbed or reacted. Now let's look at the second injection. The second injection produces a small peak, which means that some probe gas is being detected by the thermal conductivity detector, TCD. This suggests that after the first pulse, a portion of the catalyst sites are still available for absorption, but not all of them were fully saturated by the first injection. As a result, some hydrogen is still available in the system to elute and be detected. Now, after the third injection, a shorter arrow indicates that less hydrogen is being consumed during the third pulse compared to the earlier ones. This implies that the catalyst surface is nearing saturation. Fewer absorption sites are available for further hydrogen uptake. As the surface becomes more saturated with hydrogen, it becomes increasingly difficult for additional hydrogen to interact with fresh surface sites, hence reducing the amount of gas consumed. Now on the saturation stage, which is the last 3 peaks, the final injections show a saturation plateau. where the reaction is essentially complete and the catalyst has reached its maximum absorption capacity. The elute peaks do not significantly change in height, meaning that no additional hydrogen is being absorbed, and the system has reached a state where the platinum-alumina surface is fully saturated with hydrogen. The first case study was conducted utilizing static chemisorption. The sample was prepared in situ with the procedure that was mentioned previously. 2 experiments, each consisting of 10 test runs, were conducted. The first experiment used carbon monoxide gas. The second experiment used hydrogen gas. The results from these 2 experiments show that the dispersion values decrease with repeated use of the same sample. It is a good indication that sintering effect took place on our catalyst, meaning platinum particles migrated and formed a cluster of larger platinum particles on the support. Some active metals became embedded in the cluster, and only a small fraction of metal participates in the reaction. Comparing carbon monoxide and hydrogen probe gases, the dispersion value of carbon monoxide continuously decreased and eventually fell out of specification. The reason being that pulling a vacuum and applying heat was not sufficient to remove bound CO. The carbon monoxide molecule has a stronger binding affinity for metals than hydrogen molecules. In contrast, when hydrogen was used as a probe gas, the dispersion value decreased but remained within the specification. Therefore, using carbon monoxide as a probe gas could limit the number of times a catalyst can be used. The first case study using static chemisorption method on our 3 flags. Now we'll move on to the second case study, in which we investigated the impact of oxygen on metal dispersion measurements using dynamic chemisorption method on our AutoChem III. 2 experiments were conducted. The first was a controlled experiment, and the second involved an additional step where we removed the sample tube and exposed it to air for about 1 hour after the activation step. The dispersion value obtained for the controlled process and the air-exposed sample were 29% and 105% respectively. The higher dispersion value in the second experiment highlights the susceptibility of the measurement to oxygen. First, oxygen can reoxidize the sample during the cleaning process. Second, hydrogen can react with oxygen, leading to a false positive result. When comparing the 2 experimental graphs, it is clear that the control experiment took 3 injections to reach partial saturation stage. In this experiment, the graph showed above, the first injection was fully consumed. The second peak showed some hydrogen gas detected by the TCD, and the third injection approached the saturation stage. In contrast, the second experiment, the graph shown below, the first 3 injections were completely consumed, and the TCD only picked up the hydrogen signal after the 4th injection. A key takeaway is that the cleaning process after the activation step is crucial. Any trace of oxygen can reoxidize the material and react with oxygen, which will affect the measurements. Hence, if your gas cylinder is below a certain threshold, it may be a good idea to replace it. In case study 3, we look into the implications of reduction temperature on metal dispersion, the hydrogen spillover effect, and the promotion of sintering. In the first stage, we perform a temperature-programmed reduction (TPR) on platinum-alumina to obtain a temperature profile. During this, we observed 3 peaks at 85 Celsius, 170, and 367 Celsius. Next, we conducted multiple dynamic chemisorption experiments to compare the dispersion results. Additionally, we took one step further to promote sintering by reducing the sample beyond the calcination temperature. Before conducting a TPR experiment, it is important to know the calcination temperature of your material. After conducting multiple post-chemisorption experiments at different reduction temperatures, the dispersion values increased as the reduction temperature rose up to 500 Celsius. Reduction temperatures of 100 and 200 Celsius showed low dispersion values, suggesting the presence of platinum oxide on the surface, which likely limited absorption after activation. Overall, the absorption uptake peaked at 500 Celsius. Beyond this temperature, the dispersion value began to drop, indicating the onset of sintering. As mentioned earlier, when sufficient energy is provided to platinum particles, they begin to vibrate and migrate, forming larger clusters, which leads to a loss of catalytic activity. Lastly, no hydrogen spillover effect was observed in our experiments. The results showed that static chemisorption using CO and hydrogen as probe gases produced similar dispersion values. Additionally, the dispersion values were in good agreement with those obtained from dynamic chemisorption. The advantage of the dynamic chemisorption method is that it requires significantly less time compared to static chemisorption. Case study 1 demonstrated that carbon monoxide gas limited the number of cycles the same material could undergo due to its strong binding affinity to the metal. In contrast, hydrogen as a probe gas exhibited a reusability characteristic on the same material due to its moderate binding affinity, which can be disrupted more easily. Case study 2 highlighted the presence of oxygen can affect dispersion measurements. A key recommendation for our viewers is that use a high purity inner gas to purge the system after the activation process to minimize such effects. Lastly, case study 3 showed that the dispersion values were influenced by the reduction temperatures. As expected, pretreatment at temperatures at beyond the calcination threshold resulted in platinum particle migration, which effectively reduced the number of active sites available for catalytic activity. Thank you all so much for joining today's webinar. I appreciate your time and attention, and I hope you found the session helpful. If you have any questions or need further information, feel free to reach out.